Here's a real-time data challenge that's everywhere in the tech world. Find median from data stream. It's a Pattern Mastery 100 classic and a favorite at Google, Amazon, and Facebook because it tests your knowledge of heaps, streaming algorithms, and dynamic data structures. Over 40% of candidates get stuck designing for both fast inserts and instant median queries. Let's make sure you're ready to impress. Let's conquer Find Median from data stream using the basic approach, a proven strategy for building robust, interview-ready solutions to complex streaming problems. Let's break it down. Design a data structure with two methods. Add an integer to the data stream. Return the median of all current elements. Input, sequence of numbers, one at a time. Output, the median after each query. Here's a real-world example. Suppose you're building a live dashboard for financial transactions, and you need to report the median transaction value in real time, no matter how many numbers arrive or what order. Interviewers might ask, how would you design a system to track the real-time median in a large, ongoing event log? Let's assess it. What's tricky? Median queries must be fast, O1 or O log n, and so must inserts. You need to handle an unlimited number of incoming numbers, so no sorting or rebuilding the list each time. Keeping the data split evenly for medians is the key. Think step by step. Use two heaps. Max heap, left side, stores the smaller half of the numbers. Minute heap, right side, stores the larger half. The max heap lets you instantly get the largest of the smaller half. The min heap gives the smallest of the larger half. Balance the heaps so that their sizes differ by at most one median. If both heaps have the same size, median is the average of the two tops. If one heap is bigger, median is its top. Let's go deeper. When adding a new number, if it's less than or equal to max heap's top, add to max heap, else, min heap. Balance, if any heap has more than one extra element, move its top to the other heap. This balancing act ensures that extracting the median is always O1 or O log n. Edge cases. First number, just add. Even or odd total numbers, median logic switches accordingly. Duplicates and negatives are handled naturally. Here's the structure. Initialize two heaps, max heap, invert values for Python's min heap, and min heap. On add num. If max heap empty or num is less than or equal to top of max heap, push into max heap. Else, push into min heap. Rebalance if heaps differ in size by greater than 1, on find median. If size is equal, median is average of tops. Else, median is the top of the larger heap. Now let's implement the sorted list approach, inserting each value in its correct position so we can directly compute the median at any time. Constructor we declare a list that will always stay sorted, no matter how many numbers get added. We initialize the list as an empty array list, ready to store values in sorted order. Step 1. Adding a number. We use binary search to find where this new number should go. Binary search gives us the correct sorted position in O log n time. When binary search doesn't find the value, it returns a negative number encoding the insertion point. We convert that to the correct index. We insert the number into the list at the exact sorted position. This keeps the list sorted, but requires shifting elements, which is why insertion is ON. Step 2. Finding the median. We get the number of elements currently in the data structure. If the list has an odd number of elements, the median is simply the middle element. If it has an even number of elements, we take the two middle values and average them to get the median. And that's how this algorithm works. It first inserts each number into a sorted list using binary search, then reads the middle elements directly to compute the median. Efficient, simple, and elegant. Let's test our median finder with this sequence. We're inserting numbers one by one and checking the median after each step. After inserting 1 and 2, the data is 1, 2, median is the average, 1.5. After inserting 3, the data becomes 1, 2, 3, median is the middle value, 2.0. And that's exactly what the program outputs, perfectly matching the expected results. So, our implementation is correct. The stream is processed properly and the medians are computed accurately. Now let's implement the two heaps method, balancing a max heap and min heap to keep the lower and upper halves separated for fast median retrieval. This approach keeps the lower half of numbers in a max heap and the upper half in a minute heap, letting us find the median efficiently. Constructor, setting up two heaps small stores the smaller half of the numbers, but we keep it as a max heap. This lets us quickly access the largest value in the lower half, important when computing the median. Large stores the larger half of the numbers as a min heap, so we can always access the smallest value in the upper half. We initialize small as a max heap by reversing the order. And large is a normal min heap, Java's default. Add num, insert a number while keeping balance. We always begin by pushing the new number into the max heap. This ensures that new values enter the lower half first. We then move the largest value from the lower half, small, into the upper half, large. This step keeps the heaps ordered correctly. Finally, we rebalance. If the upper half grows bigger than the lower half, we move its smallest value back into the lower half. This keeps both heaps at equal size or with small holding one extra. Find median. Retrieving the median in O1. If the max heap has one extra value, its top element is the median, the center of the data. If the heaps are the same size, we take the average of the two middle values, the top of each heap. And that's how this algorithm works. It first organizes numbers into two balanced heaps, then retrieves the median instantly from the tops of those heaps. Efficient, simple, and elegant. Let's run through this test again to confirm the behavior. We add numbers to the stream and query the median along the way. After adding 1 and 2, the values are 1, 2, so the median is 1.5. Adding 3 gives 1, 2, 3, making the median the middle value, 2.0. And that's exactly what our program returns, matching the expected output. So, our implementation is correct. The median calculation works consistently across test runs. Real-time data never waits. Find median from DataStream shows whether you can keep inserts fast and still answer median queries instantly. A perfect blend of heaps and smart balancing. Let's do a recap. We designed a structure with two operations: add a number and get the current median. Conceptually, it's about maintaining the middle of an ever-growing set without resorting everything each time. The trap is rebuilding or sorting on every insert. It's too slow. Instead, we split the data into two sides so we can grab the middle on demand. That gives us quick inserts and O1 median reads. Our plan uses two heaps, a max heap for the smaller half and a min heap for the larger half. Every new number goes to the appropriate side, then we rebalance so sizes differ by at most 1. If both heaps are equal in size, the median is the average of their tops. If not, it's the top of the larger heap. We followed that blueprint precisely, routing each incoming number to the correct heap, rebalancing when needed, and reading the median from heap tops. We ran it on LeetCode without any errors. We verified the logic through multiple runs, odd and even counts, negatives, duplicates, and mixed orders. The medians matched expectations, and all test cases passed. The takeaway: separate, balance, and peak. By keeping two heaps in lockstep, you get streaming inserts with immediate, reliable medians, exactly the performance profile real-time systems demand.